Science does not erase wonder, it refines it. Knowing that a star's light has traveled for 10 billion years does not make it less beautiful. It makes its survival miraculous. Knowing that the atoms in our bodies were forged in ancient suns does not reduce us to dust. It ennobles us as stardust that can think. The philosopher Alan Watts once said that we are the universe playing hide and seek with itself. Perhaps that is true. Perhaps consciousness arose so that the cosmos could briefly look in a mirror. When the James Webb Telescope captures a field of galaxies, it is not just taking a picture of the past, it is showing us the scale of our own becoming. Each image is a reminder that we are latecomers to a universe already ancient, but participants nonetheless. That awareness brings both humility and pride. Humility in our scale, pride in our ability to see. Every generation that looks deeper into the universe inherits not only new data, but a new form of hope. Hope that knowledge can replace fear. Hope that understanding can unite where ignorance divides. Hope that somewhere, amid the billions of worlds, there might be others looking back. And even if there are not, the search itself gives purpose. To seek is to exist fully, to participate in the great unfolding. In the end, the cultural impact of cosmic discovery is not about what we find, but what we become in the process of searching. We are learning to think in cosmic time, to care in cosmic scale. Astronomy does not make us insignificant, it makes us aware. And awareness, once awakened, does not fade. It changes art, faith, language, and imagination. It changes what it means to be human. Perhaps the ultimate legacy of our telescopes will not be the images they capture, but the vision they inspire. A vision that reminds us, across every culture and century, that wonder is our most universal language. The universe will go on expanding long after we are gone. Stars will rise and fall. Galaxies will collide and dissolve. Thus, the more precisely we measured, the more we realized how little we understood. Our greatest achievement, mapping the cosmos, revealed that most of it cannot be seen. Still, the tools grew sharper. Ground-based projects like the Atacama Cosmology Telescope and the South Pole Telescope continued to refine CMB measurements, while massive surveys like DESI, Dark Energy Spectroscopic Instrument, began to record redshifts for tens of millions of galaxies, tracing how dark energy influences their distribution. DESI's work is ongoing, a collaboration of hundreds of scientists across the globe. Its robotic system can align 5,000 optical fibers simultaneously, collecting spectra from thousands of galaxies every night. Each observation adds another pixel to the cosmic map, another note to the symphony of expansion. Through these efforts, humanity is constructing a 3D model of the universe with unprecedented detail, a simulation so vast that it approaches the scale of reality itself. This is what it means to fly through galaxies, not in a spacecraft, but through data, through light translated into motion, sound, and image. Each coordinate, each wavelength, becomes a waypoint in a cosmic journey billions of years long. Technology has made the invisible visible. Supercomputers now render the evolution of the universe from its birth to today, using equations of gravity, dark matter, and gas dynamics to recreate the cosmic web. In these simulations, such as the Illustris and Eagle projects, galaxies form, collide, and merge in exquisite detail. Watching them is like observing time itself take shape. But even in the most advanced simulations, the mystery persists. Why is the universe structured this way? Why filaments? Why voids? Why does it accelerate instead of slowing down? Every answer leads to deeper questions. What we do know is that gravity alone cannot explain it. There is something else, an unseen hand shaping the large-scale structure. It may be the influence of dark energy or something stranger still, an unknown aspect of space-time itself. This search has turned astronomy into a hybrid of science and philosophy. The instruments are precise, the data immense, but the implications stretch beyond physics into questions of existence itself. If the observable universe is only a small fraction of all that exists, what lies beyond its edge? If cosmic inflation stretched space-time faster than light in the first instant after the Big Bang, could there be regions forever disconnected from us, entire universes with their own laws of nature? We pause, suspended amid this galactic ocean. Every pinprick of light below is a galaxy, not a star. Each contains hundreds of billions of suns, and each sun may host worlds. From here, the concept of home begins to blur. There are no up or down directions, only the endless geometry of gravity and light. We surge onward. Galaxies begin to cluster in massive filaments, cosmic highways of luminous matter stretching across billions of light years. Between them lie voids, immense hollows where almost nothing exists. These voids are not empty, but nearly so, just a few lonely atoms per cubic meter. If you placed a star there, it would shine alone for eternity. The largest of these is the Boötes void, a dark expanse nearly 330 million light-years across, containing only a handful of galaxies. Flying through it feels like traversing the space between thoughts. The galaxies around its edges form a kind of wall, where matter, shaped by primordial fluctuations, gathered under gravity's patient pull. We break free from the void's silence and emerge into structure again, a luminous web spanning all directions. Clusters connect to superclusters, superclusters connect to filaments, and filaments weave the cosmic web. It is a living architecture, frozen in slow motion. If you could speed up time, you would see galaxies flow along these threads like rivers, merging and colliding in a gravitational ballet billions of years long. The scale becomes incomprehensible. We have now traveled billions of light years from our starting point. The visible universe around us resembles a glowing sphere, a three-dimensional map of all known galaxies. The densest regions are the great clusters, Coma, Perseus Pisces, Hercules, Shapley. Between them stretch filaments tens of millions of light years thick. It is a cosmic coral reef, alive with light. And yet, even here, in this unimaginable immensity, there is order. Patterns emerge, spirals, chains, nodes, all shaped by the same physical laws that govern the orbit of our moon. The gravitational equations of Isaac Newton and Albert Einstein still hold true, even across these titanic distances. The same mathematics that describe an apple falling to Earth describe galaxies falling into one another. We move still farther, faster now, until galaxies blur into faint mist. Their light merges into the diffuse glow of the cosmic background, a universal fog that fills all of space. This faint radiation is the oldest light we can see, the cosmic microwave background. It is not light from stars or galaxies, but from the universe itself when it was young, only a few 100,000 years old. Approaching it feels like reaching the dawn of time. The temperature of this radiation is just 2.73 Kelvin, a whisper above absolute zero. It is everywhere, isotropic, yet slightly uneven. Its faint ripples the fingerprints of the first cosmic. And though our voices will fade, the light we've seen will continue on, crossing the void, touching other horizons, reflecting back the truth we finally learned, that the cosmos was never distant. It was always within. Telescopes is a record of where and when it came from. The cosmos does not give up its secrets easily, but it leaves clues in the faintest details of light. Astronomy is, at its heart, the science of reading those clues. Every star, every galaxy, every distant quasar writes its own signature into light. The spectrum of that light, the way it spreads into color, tells us its temperature, its composition, and most importantly, its motion. When light stretches toward red, it means the source is moving away. When it shifts toward blue, it is approaching. This phenomenon, known as redshift, became the ruler of the cosmos. It allows astronomers to measure not only how far galaxies are, but how fast the universe itself is expanding. When Edwin Hubble plotted the redshift of galaxies against their distance, he discovered a simple, elegant truth. The farther away a galaxy is, the faster it recedes. The line on his chart was not random, it was the blueprint of expansion. This discovery transformed light into a kind of time machine. Every redshifted spectrum is a memory, a snapshot of the universe at a younger age. A galaxy seen at a redshift of 1 appears as it was half the universe's current age. A redshift of 10 reveals light that began its journey when the first stars ignited. Beyond a redshift of 15 lies the cosmic dawn, the era when galaxies themselves first emerged from darkness. But measuring redshift requires precision. It demands instruments so sensitive that they can detect the shift of a single spectral line across billions of light years. To achieve this, astronomers built spectrographs, machines that split light into its component colors with exquisite accuracy. Mounted on massive telescopes like Keck in Hawaii, VLT in Chile, and Subaru in Japan, these instruments became humanity's measuring sticks for the universe. They revealed a pattern larger than anyone had imagined. NED. Galaxies were not scattered randomly. They formed clusters, gravitational families bound together in groups. Those clusters linked into filaments, long chains of matter stretching across millions of light years. Between them lay vast cosmic voids, regions nearly empty of galaxies. This structure, when mapped in 3 dimensions, resembled a cosmic web, a vast sponge-like pattern where matter gathered along thin strands, leaving dark gaps in between. The universe, it turned out, was not uniform. It was a structure built from tension, gravity, and time. The first detailed maps of this web came from ambitious surveys like the Sloan Digital Sky Survey, SDSS. Beginning in 2000, SDSS used a 2.5-meter telescope in New Mexico to systematically photograph and measure millions of galaxies. Over the years, its data became a cosmic atlas, showing not only where galaxies were, but how they moved, how they evolved, and how the universe itself had changed. Each galaxy, plotted as a single point, formed part of an immense structure, a honeycomb of existence stretching across the observable universe. The image was both humbling and soul. Music inspired by Hubble's images fills concert halls, while documentaries narrate cosmic birth as if it were an ancient hymn. The scientific and the sacred have begun to converge, not in dogma, but in shared wonder. For centuries, religion offered the stars as divine symbols. Now, science offers them as living evidence of creation in motion. Both point to the same truth, that existence is rare, fragile, and astonishing. The images from Hubble and Webb have become modern icons, seen by billions, reshared endlessly, each one a silent prayer of perspective. A single deep field can bring a person to tears, not from sadness, but from the realization that the human story is part of something immeasurably vast. In classrooms, children now learn not only the names of planets, but the distances between galaxies. They grow up with the knowledge that the Milky Way is one of hundreds of billions, and that light itself has a speed, a finite heartbeat through which we glimpse eternity. That understanding changes how a generation sees itself. It teaches humility without despair, curiosity without arrogance. Astronomy has become a quiet teacher of empathy. The cosmic perspective reminds us that we are all from the same origin, all made of the same elements, all fleeting against the same cosmic clock. Seen from space, there are no borders, no nations, no divides, only a single planet suspended in starlight. This realization, known as the overview effect, has transformed not only astronauts but cultures. Art reflects it, literature absorbs it, politics resists it, and then, slowly, yields. The farther we see, the harder it becomes to cling to smallness. The fragile blue dot of Earth, once the center of myth, now floats as one among countless worlds. And yet it remains unique, our only known oasis in the cosmic desert. That image, Earth from afar, may be the most powerful photograph ever taken. It reminds us that in all the galaxies we've mapped, in all the cosmic fields we've charted, we have found no second home. It humbles our ambitions and refines our responsibilities. Exploration, then, is not escape. It is reflection. Every mission outward deepens the meaning of home. The cultural ripple of space exploration is also emotional. The sight of JWST's first deep field in 2022 sparked a collective reaction around the world, a shared intake of breath. People who had never studied astronomy suddenly felt part of the discovery. Transformed not only astronomy, but human perspective. It shattered the comforting illusion of a static cosmos and replaced it with a dynamic, evolving universe. Space was not still. It was alive, stretching and changing across incomprehensible scales of time and distance. By the 1930s, the old idea of a finite, self-contained Milky Way had vanished. Astronomers now spoke of galaxies as the fundamental building blocks of the universe. Each galaxy contained hundreds of billions of stars, separated by vast intergalactic distances. Between them lay immense voids, regions of near-perfect emptiness. This revelation also birthed a new way of thinking about our place in the cosmos. For centuries, humanity had believed itself near the center of creation, first at the heart of the Earth, then within the solar system, and later within the galaxy. Now, with each scientific advance, that sense of centrality faded further. The universe seemed not built around us, but utterly indifferent to our existence. Yet within that humility came a deeper wonder. If life could arise here, under these fleeting conditions, could it not arise elsewhere, among the billions of suns beyond? Hubble's discovery also marked the dawn of modern observational cosmology. It paved the way for a new generation of instruments, radio telescopes, space observatories, and eventually space-based missions that would peer far beyond the visible spectrum. The quest to map the universe had begun. But in the 1920s and 1930s, this was still a fragile dream. Photography was slow, exposure times long, and telescope mirrors sensitive to temperature and wind. Astronomers often worked through sleepless nights, capturing faint smudges of light on glass plates, then developing them in darkrooms before dawn. The universe revealed itself not in sudden epiphanies, but in quiet increments of data, charted patiently over year. Still, those early discoveries carried a poetic weight. Each new galaxy measured, each faint spiral resolved, was another revelation that the universe had no walls. The cosmos was expanding, not merely in space, but in meaning. Humanity had crossed a threshold, from seeing the sky as a dome to seeing it as infinity itself. The great debate had been settled, not by argument, but by observation. Curtis's vision of island universes had proven true, yet even he could not have imagined the sheer magnitude of what lay ahead. The Milky Way, once thought to encompass everything, was now one of hundreds of billions. The known universe had grown from a single island into a vast archipelago without end. In the decades that followed, the idea of an expanding universe would lead to profound new questions. If it is expanding, what started it? What existed before? These questions would lead inevitably to the concept of the Big Bang, the notion that the universe had a beginning in time, that everything we see today was once compressed into an unimaginably dense, hot state. Some theories suggest that inflation never truly ended, that even now, far beyond our horizon, new universes are being born in a vast cosmic sea, each one a spark expanding into its own space-time, forming its own laws of physics. Ours may be just one of countless fires burning across an infinite dark. If that is true, then we are not the center of the universe. We are not even the center of a universe. We are a single flicker in a field of eternal creation. And yet, in that smallness, there is grandeur, because even if we are one among countless, we are aware. The universe has produced something that can look back at itself and wonder why it exists at all. The farther our instruments reach, the more the cosmos seems to blur into abstraction. Galaxies become smears, then points, then faint noise. At the very edge, light itself fades, not because it stops existing, but because the fabric of space stretches it into invisibility. Beyond a certain point, wavelengths grow so long that they no longer interact with matter. They become part of the slow hum of entropy, the final equilibrium toward which everything drifts. That is the universe's distant future, one of dimming and dispersal. Galaxies will drift apart faster than their light can travel. Stars will burn out, one by one. The night sky will fade until only black holes remain, slowly evaporating into nothing. The cosmic background will cool further, its temperature falling ever closer to absolute zero. And yet, even then, something of us remains, our questions, our awareness, our brief act of looking outward. For all its vastness, the universe is not infinite in memory. It will forget everything. but for a few moments in cosmic time, it has remembered itself through us. We turn now, gazing back across the light years we have traveled. The cosmic web unfolds beneath us like a living organism, clusters pulsing with starlight, filaments shimmering faintly against the dark. Every galaxy is a heartbeat, every cluster a thought. The universe seems almost conscious in its complexity. We pass again through superclusters, voids, and the luminous bridges of matter connecting them. From the grandest scales, structure begins to fade. Galaxies blur into patterns, patterns into haze, haze into colorless fog. We return toward the familiar, but it no longer feels small. The Milky Way, once vast, now seems like a single neuron in an infinite mind. This is the paradox of perspective. The closer we come home, the larger everything becomes. At last we find our galaxy again, spiraling quietly in the darkness. The sun glows within one of its arms, a single point in the grand tapestry. Around it, Earth turns, fragile and luminous, wrapped in a thin blue film of air, soul. Music inspired by Hubble's images fills concert halls, while documentaries narrate cosmic birth as if it were an ancient hymn. The scientific and the sacred have begun to converge, not in dogma, but in shared wonder. For centuries, religion offered the stars as divine symbols. Now, science offers them as living evidence of creation in motion. Both point to the same truth, that existence is rare, fragile, and astonishing. The images from Hubble and Webb have become modern icons, seen by billions, reshared endlessly, each one a silent prayer of perspective. A single deep field can bring a person to tears, not from sadness, but from the realization that the human story is part of something immeasurably vast. In classrooms, children now learn not only the names of planets, but the distances between galaxies. They grow up with the knowledge that the Milky Way is one of hundreds of billions, and that light itself has a speed, a finite heartbeat through which we glimpse eternity. That understanding changes how a generation sees itself. It teaches humility without despair, curiosity without arrogance. Astronomy has become a quiet teacher of empathy. The cosmic perspective reminds us that we are all from the same origin, all made of the same elements, all fleeting against the same cosmic clock. Seen from space, there are no borders, no nations, no divides, only a single planet suspended in starlight. This realization, known as the overview effect, has transformed not only astronauts but cultures. Art reflects it, literature absorbs it, politics resists it, and then, slowly, yields. The farther we see, the harder it becomes to cling to smallness. The fragile blue dot of Earth, once the center of myth, now floats as one among countless worlds. And yet it remains unique, our only known oasis in the cosmic desert. That image, Earth from afar, may be the most powerful photograph ever taken. It reminds us that in all the galaxies we've mapped, in all the cosmic fields we've charted, we have found no second home. It humbles our ambitions and refines our responsibilities. Exploration, then, is not escape. It is reflection. Every mission outward deepens the meaning of home. The cultural ripple of space exploration is also emotional. The sight of JWST's first deep field in 2022 sparked a collective reaction around the world, a shared intake of breath. People who had never studied astronomy suddenly felt part of our flight. Then is both physical and philosophical. We have moved outward through layers of cosmic structure, but inward through layers of meaning. The Milky Way was our cradle. The cosmic web is our cathedral. Between them stretches everything we have ever been and will ever know. As we prepare to cross into the ultimate unknown, the question changes. No longer how far can we see, but what happens beyond what can be seen? The answer lies in the light that remains, the faint relic radiation, the ghostly echo of the universe's birth, waiting just ahead. And so we continue forward, toward that final frontier where the first light still glows, stretched thin by time, whispering of beginnings. Because the journey does not end with galaxies, it ends with the universe itself remembering how it began. We drift in silence, Ahead lies the oldest light that still exists, the cosmic microwave background, the last visible trace of the universe's birth. It surrounds us on all sides, faint and uniform, like the fading afterglow of a fire that once burned brighter than 1,000 suns combined. For a long moment, we simply float there. This is the cosmic horizon, the farthest edge of sight. No telescope can look beyond it, because beyond it, light itself has never reached us. What lies there is not hidden by dust or distance, but by time itself. The background hum we now approach began 13.8 billion years ago. Before this moment, the universe was not transparent. It was a storm of radiation and plasma, an ocean of charged particles scattering light in every direction. No image, no structure, no clarity. Then, at a temperature of roughly 3,000 Kelvin, protons and electrons combined to form the first atoms. The fog lifted, light broke free. That light has been traveling ever since, stretched by the expansion of space until its waves are now microwaves, invisible to human eyes yet still filling the sky. We are not merely seeing the beginning, we are touching the oldest memory in existence. Each photon of this relic radiation carries a message from the infant cosmos, frozen at the moment when it first became visible. In every direction, it tells the same story, that everything we know, every galaxy and star, emerged from that single, radiant dawn. If we could translate its faint hum into sound, the early universe would not roar, it would sing. A low, steady chord, resonating across the void, the music of expansion itself. We glide closer to the texture of this ancient light. It is not perfectly smooth. Subtle ripples run through it, tiny variations in temperature and density, 1 part in 100,000. These are the fingerprints of the universe's first structures, the seeds from which galaxies, clusters, and superclusters would eventually form, shown in classrooms and shared across the world. They were not just data, they were windows into existence itself. Yet even as Hubble revealed the visible universe, astronomers hungered for more. Visible light was only a fraction of the story. Much of the cosmos lay hidden, in wavelengths beyond human sight, veiled in infrared. To see the earliest galaxies, whose light had stretched and reddened as the universe expanded, scientists needed a new instrument, one capable of seeing heat itself. That next chapter began with the James Webb Space Telescope. Launched on December 25, 2021, Webb was not merely a successor, it was a revolution. Where Hubble orbited close to Earth, Webb would travel 1 million miles away to a region known as the L2 Lagrange point, where gravitational forces balance perfectly, allowing the telescope to remain stable and cold. Webb's mirror was vast, 6.5 meters across, made of beryllium and gold, folded like origami to fit inside its rocket. When deployed, it unfurled with mechanical precision, its 18 hexagonal segments aligning into a single flawless surface. Beneath it, a sunshield the size of a tennis court protected it from sunlight and heat, keeping its instruments at temperatures colder than space itself. Where Hubble saw the visible, Webb saw the invisible. Its infrared eyes pierced cosmic dust, revealing newborn stars inside nebulae and ancient galaxies whose light began its journey nearly 13.5 billion years ago. In its first images, released in July 2022, Webb captured galaxy clusters warped by gravity, light stretched and bent by massive unseen structures. It revealed the SMACS 0723 deep field, a dazzling window packed with thousands of galaxies in a single frame. Each speck was an entire universe of its own. The telescope could also detect the faint signatures of elements in exoplanet atmospheres, tracing the chemical fingerprints of water, carbon, dioxide, and methane, key ingredients of life. It could peer into the hearts of star nurseries and trace the delicate filaments of cosmic evolution from the first stars to modern galaxies. Every image from Webb carried the same silent astonishment that Hubble once inspired, but magnified beyond imagination. For the first time, humanity was not just seeing galaxies as they were, it was seeing them as they had been at the dawn of time itself. While Webb probed the universe's infancy, another observatory was mapping its present. High above Earth, The Gaia Space Observatory, launched by the European Space Agency in 2013, turned its gaze not outward but inward toward our own Milky Way. Gaia's mission was cartography on a galactic scale, using precise measurements of parallax and motion, Gaia. And so, philosophy and physics converge. When cosmologists describe space-time curvature or quantum fields, they are also, unknowingly, describing awe. Every mathematical symbol is an act of reverence. Every experiment, an echo of that first human who looked at the stars and wondered. Perhaps the ultimate discovery will not be a new galaxy or a deeper field, but an understanding of why beauty and truth feel so intertwined. Why the same equations that describe gravity also generate wonder. The philosopher Immanuel Kant once said that two things filled him with ever-increasing admiration: the starry heavens above and the moral law within. Centuries later, that connection remains. The heavens remind us of what we are not. The moral law reminds us of what we could be. The cosmos does not need our meaning, but we do. Each time we look outward, we rediscover our own fragility and our own potential. Astronomy's greatest gift is not knowledge, it is perspective. When we measure the distance to a distant galaxy, we are also measuring the distance between what we are and what we wish to become. Our telescopes may one day reach the edge of the observable universe, but the true horizon lies within consciousness itself. The ability to imagine beyond what we can see, to wonder about what might exist even without proof, is what keeps the story alive. The universe may be silent, but our questions give it voice. Every discovery, every image, every map is a conversation between mind and cosmos, a dialogue that began when the first spark of awareness flickered in the dark. And somewhere within that conversation lies the bridge to the next phase of exploration. Because after all the philosophy, after all the reflection, there remains a simple, irresistible truth. We still want to see it all. Not just to imagine it, but to experience it, to travel through it, to follow the light as far as it will tell, jwst, until it fades into the first dawn. And that is where the journey turns from theory to vision, from understanding the universe to flying through it. We begin at home. The Milky Way stretches across the night sky like a river of light, hundreds of billions of stars bound together in a slow galactic dance. From within, it seems endless. From above, it is a spiral, delicate arms of gas and dust coiling around a bright nucleus where a supermassive black hole, Sagittarius A, lies hidden behind veils of starlight. Perhaps that is the real reason the universe exists at all, to know itself, even for a brief instant, through beings capable of wonder. If so, then our search for meaning has already succeeded. Every photon we capture, every galaxy we map, every hypothesis we form, each is a continuation of the same cosmic story, the transformation of chaos into clarity, darkness into perception. And though the night sky is indifferent, it is also generous. It gives us perspective, it gives us humility, it gives us the truth that we are both infinitely small and infinitely significant, because we can know the difference. Science tells us that one day the stars will fade, the galaxies will drift apart, and even light will surrender to time. But awareness, the act of knowing, of marveling, may be the universe's most enduring echo. Perhaps in some far future, in another corner of creation, consciousness will rise again and rediscover the same truth, that beauty is not a property of matter, but of meaning. When Edwin Hubble proved that other galaxies existed, he expanded our universe. When we launched Hubble's telescope, we expanded our perception. When Webb opened its golden eyes, we expanded our sense of time itself. Each expansion has not been outward, but inward. The stars did not move, we did. And so the horizon remains, not as a border, but as an invitation. Every discovery brings us closer, not to an ending, but to a beginning that never stops unfolding. In the soft hum of the cosmic background, in the spiral arms of distant galaxies, in the faint glow of nebula where new suns are born, the universe keeps whispering the same message. You are part of me. We listen, not with ears, but with understanding, and that understanding is enough. So let the light keep traveling. Let the telescopes keep turning. Let curiosity remain our constant motion through time. Because even when the stars grow cold, the memory of seeing them will still warm the universe. We are that memory, the fleeting moment when existence became aware of itself and called it wonder. But for a brief interval, in one small corner of space-time, awareness bloomed and called itself human. That will always mean something, because through that awareness, the universe became not just vast, but beautiful. Beauty is not in the stars themselves. It is in the act of seeing them. We have spent centuries trying to measure the universe, its distances, its expansion, its age. Yet all our instruments, from Galileo's first telescope to the gold-mirrored eyes of James Webb, have been extensions of something older, the human desire to look beyond what is known. That desire is what makes the cosmos ours, not through ownership, but through understanding. The universe does not bend toward us. It does not speak our language, share our purpose, or need our attention. And yet, by some quiet miracle, we have learned to read its light. Every equation of physics, every map of galaxies, every image of a distant nebula, these are translations of silence. The cosmos has no words, but we have given it meaning. That, perhaps, is our most remarkable creation. Standing at the edge of the observable universe, we confront a paradox. We can see nearly 46 billion light-years in every direction, yet we cannot touch a single one of those galaxies. We are surrounded by what we can never reach. But maybe the point was never to reach. It was to see. The cosmic horizon is not a wall, it is a mirror. It reflects not the end of the universe, but the beginning of awareness. When we look outward, we see time unfolding in reverse, the past made visible through distance. But when we look inward, we see the present, alive with comprehension. Between those two views, the ancient and the immediate, lies everything that makes us human. Our telescopes, our satellites, our equations, they are all mirrors facing the infinite, showing us fragments of ourselves scattered among the stars. We built them to see creation. They revealed participation. We are not observers of the universe, we are expressions of it. Atoms forged in ancient suns learned, through consciousness, to wonder where they came from. Hydrogen became memory, carbon became thought, light became understanding. The boundaries between observer and observed will blur as machines learn to see patterns beyond the reach of human perception. At the heart of this transformation stands AI-assisted astronomy. The universe is vast beyond imagination, its data vaster still. A single survey from an advanced telescope can generate petabytes of information, images, spectra, motion data, and noise. No team of humans could ever process it all, so we've taught the machines to look with us. Algorithms now comb through the flood of data, recognizing galaxies, identifying supernovae, and tracing cosmic filaments. They distinguish the subtle redshifts of early galaxies and flag anomalies that might otherwise go unnoticed. New quasars, faint exoplanets, or unexplained gravitational lensing events. Each discovery becomes both a product of human curiosity and machine precision. The Vera C. Rubin Observatory, perched atop Cerro Pachón in Chile, will soon begin its legacy survey of space and time, LSST, the most ambitious optical survey in history. Over 10 years, it will scan the entire southern sky every few nights, capturing billions of galaxies, stars, and transient phenomena. Its camera, containing over 3.2 billion pixels, is the largest ever built. Each image will be so detailed that a single night's data would take weeks to analyze by traditional means. Instead, AI will sift through it instantly, detecting the flicker of distant supernovae or the subtle motion of near-Earth asteroids. The result will be a time-lapse of the universe, a cosmic film spanning 10 years, showing how galaxies evolve, how stars die, and how the sky itself changes. It will be the closest thing to watching creation in motion. Meanwhile, in orbit, the Nancy Grace Roman Space Telescope, sometimes called Hubble's wide-eyed successor, will survey vast swaths of space in infrared, combining Webb's depth with panoramic scale. Roman's detectors will be able to capture hundreds of times the area of Hubble's field of view, mapping billions of galaxies in exquisite detail. Its primary mission: to probe dark energy, the invisible force accelerating cosmic expansion. By comparing distant supernovae, weak gravitational lensing, and large-scale structure, Roman will measure how the expansion rate of the universe has changed over time. If dark energy is constant, the cosmos will expand forever. If it evolves, the universe's fate could be far stranger. Yet Roman and Rubin are just the beginning. The Square Kilometer Array, SKA, a network of thousands of radio antennas stretching across South Africa and Australia, will listen to the universe in wavelengths invisible to any other telescope. It will map hydrogen, the most abundant element in the cosmos, across billions of light years, tracing how matter gathered into the first galaxies after the Big Bang. By detecting the faint 21-centimeter emission of neutral hydrogen, SKA will produce a 3-tauan. From this distance, all the complexity of human history, our empires, our wars, our art, fits inside a single pixel of light. And yet, within that pixel lies the only known consciousness in the cosmos, the only eyes that have ever looked upon this vastness and named it beautiful. Perhaps that is what makes our smallness sacred. We are not spectators of the universe. We are participants in it. We are made of its dust, moved by its gravity, illuminated by its stars. Every breath we take is the echo of fusion, every heartbeat a rhythm older than the galaxies themselves. The journey outward was a search for scale. The journey home becomes a search for meaning. The edge of observation shows us not how far we can go, but how far we've already come. From the first human who looked at the stars and wondered, to the telescopes orbiting the Earth, to the data pouring from Webb, Gaia, and Euclid, each step is a declaration that curiosity itself is cosmic. We have crossed billions of light years in thought. We have seen the beginning and glimpsed the end, and now, standing between them, we understand that the most remarkable thing about the universe is not its size, but its awareness, that for one brief epoch, matter learned to see itself. The relic radiation still hums, faint and eternal, all around us. It is not just the sound of creation, it is the sound of continuity. And as it fades into silence, one truth remains clear. The light that began long ago has reached its destination, not just in our telescopes, but in our understanding. We are the universe, witnessing its own story. The story does not end with discovery. It begins again. Each time a new instrument opens its lens, each time a new photon reaches a sensor. The universe is not static, neither is our understanding of it. From the first polished mirrors of Galileo to the golden hexagons of the James Webb Space Telescope, astronomy has always been an active iteration, each generation refining the vision of the one before it. Now, as Webb's images pour in and Gaia's stellar maps expand, a new era of cosmic observation is already unfolding. One defined not just by human hands, but by artificial intelligence, autonomous instruments, and planetary-scale collaboration. In the coming decades, the skies will be mapped in real time. New observatories, both ground and orbital, will transform our static snapshots of the cosmos into living movies, capturing the universe in motion. Profound. We could finally see the universe's skeleton, the scaffolding shaped by gravity after the Big Bang. But where did that scaffolding come from? To answer that, astronomers had to go back even further, to the oldest light in existence. In 1964, two radio engineers at Bell Labs, Arno Penzias and Robert Wilson, were testing a large microwave antenna designed for satellite communication. No matter where they pointed it, they heard a persistent hiss, a faint background noise that refused to go away. They cleaned the instrument, removed interference, even evicted a pair of pigeons nesting inside. But the signal remained. What they had accidentally detected was the cosmic microwave background, the remnant radiation from the birth of the universe. It was the afterglow of the Big Bang itself, stretched into microwaves by 13.8 billion years of expansion. This discovery was one of the most important in scientific history. It confirmed that the universe had indeed begun from a hot, dense state, and that its echoes still filled space today. The cosmic microwave background, CMB, became a cosmic fossil, a map of the universe when it was only 380,000 years old, a time when atoms first formed and light could finally travel freely through space. Decades later, satellites like COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and Planck refined that map. They revealed the CMB not as a uniform glow, but as a tapestry of tiny temperature variations, differences as small as 1 part in 100,000. Those minuscule fluctuations were the seeds of everything: galaxies, clusters, and eventually, us. Each warm spot in the CMB represented a region slightly denser than its surroundings. Gravity pulled those regions together over billions of years, forming the vast web of galaxies we see today. In that sense, the cosmic microwave background is the universe's first photograph, its birth portrait. Planck's final map of the CMB, released in 2018, is perhaps the most detailed snapshot of the early universe ever created. It shows the cosmos when it was a newborn, a smooth, glowing sphere filled with subtle ripples that would one day grow into the grand structures we now observe. From that ancient light, cosmologists could extract everything: the universe's age, its composition, its rate of expansion, and even hints of its ultimate fate. Through the study of the CMB, scientists learned that ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 5% of the universe. Another 27% is dark matter, an invisible substance that exerts gravity but emits no light. The remaining 68% is dark energy, a mysterious force driving cosmic acceleration. That democratization of the cosmos may prove to be the most profound consequence of all. Because when the stars become accessible to all, the boundaries between science and soul dissolve. We will not just study the universe, we will inhabit it, in thought, in data, in imagination. And somewhere, deep within that network of telescopes and algorithms, the same ancient question will persist: what else is out there? It is the question that drives every lens to open, every signal to be decoded, and it ensures that our story, like the universe itself, will never truly end. When humanity looked outward, it also looked inward. Every telescope, every mission, every faint photon from the edge of the universe has changed not only what we know, but who we believe ourselves to be. For thousands of years, we lived beneath a ceiling of stars and thought it was all there was. The universe was a stage, and humanity the central act. Then came the revelation that the stars were not lights above us, but suns themselves, scattered across a boundless ocean. That revelation changed our myths, our sciences, our sense of destiny. But now, in the age of deep space observation, another transformation is underway, one not of geography, but of consciousness. We are no longer the center of the universe. We are not even central to our own galaxy. And yet, paradoxically, that realization has given our existence more depth, not less. Because if meaning does not come from the universe's attention, it must come from our own. Awe becomes the new gravity that holds us in orbit with the infinite. The more we learn about the cosmos, the more it humbles us. Standing beneath a clear night sky today feels different than it did 1,000 years ago. We know what we are seeing: light that left its source before there was human history, sometimes before there was Earth. Every star is a reminder that we exist inside time's oldest memory. And yet, in that knowledge, there is comfort, because the same physics that govern galaxies also govern us. The same atoms that formed stars now shape our breath. The same gravity that binds clusters also keeps our feet on the ground. We are woven into the fabric we observe. Every discovery is a reunion. The cultural impact of that awareness has quietly reshaped art, philosophy, and even spirituality. Painters render nebulae like dreams. Poets describe galaxies as metaphors for the... But before cosmologists could explore those origins, they needed better eyes, tools capable of peering deeper into the cosmic night than any earthbound telescope could manage. The story of discovery had only begun. Because after Hubble's revelation, the next frontier wasn't proving the existence of galaxies. It was mapping them, measuring them, understanding their distribution, their age, their structure, and the invisible matter that bound them together. And to do that, humanity would have to leave Earth's surface. When Edwin Hubble revealed the universe's immensity, he gave humanity its first glimpse of the infinite. But the telescope that bore his name would one day show us what Hubble himself could only imagine. By the end of the 20th century, astronomy was no longer confined to mountaintops. Humanity had learned to lift its instruments above the atmosphere, beyond the distortion of air, light, and weather, into a realm of perfect clarity. In 1990, the Hubble Space Telescope launched aboard the Space Shuttle Discovery. It would orbit Earth for more than 3 decades, circling our planet every 97 minutes, staring deep into the cosmos from the vacuum of space. Hubble's first images were disappointing. A flaw in its primary mirror blurred its vision, scattering light and distorting focus. For a moment, the dream of seeing the universe in crystal detail seemed lost. Yet, in one of science's most daring repair missions, astronauts aboard the Space Shuttle Endeavour installed corrective optics, effectively a pair of contact lenses for the universe itself. After that, Hubble opened its eyes, and humanity saw further than ever before. Its deep-field images transformed astronomy. In 1995, scientists commanded Hubble to stare at a seemingly empty patch of sky, no wider than a grain of sand held at arm's length, for 10 consecutive days. The result was the Hubble Deep Field, an IMAW, age containing nearly 3,000 galaxies, each a unique island of stars. What had looked like emptiness was revealed as a sea of creation. It was a cosmic revelation. Every direction we looked, the universe continued endlessly. Every empty patch of darkness was filled with galaxies. Subsequent missions refined that vision. The ultra-deep field, the extreme deep field, each a longer exposure, each a deeper reach into the universe's past. Every photon captured by Hubble had traveled billions of years, leaving its source when the first galaxies were still forming. Looking outward became synonymous with looking backward in time. The telescope became a cultural icon, bridging science and art. Its images, spiral arms, glowing nebulae, dying stars, and the faint haze of distant clusters were printed on posters. Our journey starts here, within one arm of this spiral, roughly 25,000 light-years from the center. Through the haze of interstellar dust, our sun is just one of its unremarkable stars, orbiting at 500,000 miles per hour. Around it, 8 planets trace their paths through darkness, and on one of them, a thin film of life dares to look outward and imagine the impossible. We rise above the galactic plane. The stars thin into a shimmering disk. The Orion Arm, home to our solar system, merges into the wider structure. The central bulge glows with ancient starlight, dense and golden. Beyond it, the spiral arms unfurl like vast ribbons, laced with blue star clusters and crimson nebulae where new suns are born. Each point of light hides worlds, planets, moons, storms, and oceans we may never see. In this one galaxy alone, there may be more than 100 billion planets, each a question mark suspended in the dark. We pull farther back. The Milky Way becomes a grand whirlpool of light about 100,000 light-years wide. But even this colossal disk is not solitary. Nearby, the Large and Small Magellanic Clouds, 2 irregular dwarf galaxies, orbit it like loyal companions. Together, they form a small family, a gravitational microcosm of the larger cosmic hierarchy. Beyond them, faint smudges appear. The Andromeda Galaxy, 2.5 million light-years away, drifts toward us through intergalactic space. It, too, is a spiral, larger than the Milky Way, brilliant with 1 trillion suns. The 2 galaxies are destined to collide in 4 billion years, merging into a new elliptical form, sometimes called Milkomeda. But we will not wait for that. We accelerate outward. The galaxies multiply around us. The Milky Way and Andromeda belong to the local group, a small cluster of about 50 galaxies bound by gravity. Most are dwarfs, tiny ellipses or irregular shapes, dividing the larger giants. The local group spans about 10 million light-years, an island of matter adrift in a cosmic sea. We keep rising. The local group is just one node in a greater structure, the Virgo supercluster, an enormous region containing thousands of galaxy groups. Within it, galaxies swarm like fireflies trapped in invisible gravity wells. Streams of matter connect them, filaments so vast that they resemble the neural pathways of a cosmic brain. Our flight accelerates again. The Virgo supercluster merges into something even grander, the Laniakea supercluster, a titanic network spanning 500 million light-years. The name means immeasurable heaven in Hawaiian, and it is no exaggeration. Laniakea is home to 100,000 galaxies, all flowing toward a mysterious gravitational focal point known as the Great Attractor. By the early 20th century, the debate had reached its peak. In 1920, at the Smithsonian Museum of Natural History in Washington, D.C., two astronomers faced each other in what became known as the Great Debate. On one side stood Harlow Shapley, who argued that the Milky Way was vast, so vast that it encompassed everything in existence. The spiral nebulae, he believed, were merely local gas clouds inside it. On the other side stood Heber Curtis, who disagreed. He proposed that these nebulae were in fact island universes, immense galaxies like our own, lying far beyond the Milky Way's edge. For hours they argued, armed with photographic plates, sketches, and calculations. Shapley pointed to the enormous size of the Milky Way and to the distances of globular clusters orbiting its center. Curtis countered with observations of novae, stellar explosions seen in some of the spiral nebulae that appeared far too faint to be local. If these novae were truly within the Milky Way, they should have been brighter. Therefore, the nebula must be far away. No clear winner emerged that night. The audience applauded both. But behind that polite applause, the universe was quietly preparing to reveal its true scale. A few years later, at the Mount Wilson Observatory in California, a young astronomer named Edwin Hubble began studying one particular spiral, the Andromeda Nebula. Mount Wilson's 100-inch Hooker telescope was the most powerful in the world at the time. Night after night, Hubble captured photographic plates of Andromeda, examining them for any signs of variable stars, stars that brightened and dimmed over time. Among those stars were a special kind known as Cepheid variables. They pulsed rhythmically, and that rhythm revealed their true brightness. By comparing how bright they appeared from Earth with their intrinsic brightness, astronomers could calculate their distance. It was the Cepheid, the universe's first reliable measuring stick. When Hubble analyzed Andromeda's Cepheids in 1923, his calculations stunned him. The numbers placed Andromeda not within the Milky Way, but nearly 1 million light-years away, far beyond the galaxy's edge. Later refinements would extend that distance to over 2 million. Either way, it was irrefutable. Andromeda was its own galaxy, not a nearby nebula. In that moment, the universe exploded in size. What humanity once believed was everything suddenly became just one island in an immeasurable cosmic ocean. The implications were staggering. If Andromeda was another galaxy, then the other spirals visible across the sky were likely galaxies too, each containing billions of stars, perhaps billions of worlds. The universe had multiplied by hundreds of billions overnight. Hubble continued his work, systematically measuring the distances and velocities of galaxies. He noticed something else remarkable. Almost every galaxy appeared to be moving away from us. The farther it was, the faster it receded. This relationship, now known as Hubble's law, became the first direct evidence that the universe itself was expanding. Tracked over 2 billion stars, recording their positions, brightness, and movements with accuracy so fine it could detect the width of a human hair from 2,000 kilometers away. Its data built the most detailed three-dimensional map of our galaxy ever created, a living model of the Milky Way's structure, dynamics, and evolution. Every few years, Gaia released new data drops, each expanding the known stellar landscape. With these releases, astronomers could watch the galaxy breathe, clusters moving, stars orbiting, spiral arms rotating. But Gaia's influence went beyond our galaxy. By tracing the motion of stars, scientists could infer the gravitational pull of dark matter, the invisible scaffolding that shapes galaxies. It revealed tidal streams, stellar remnants of galaxies long ago consumed by the Milky Way. It showed that our galaxy was not a static island, but a restless, merging, evolving structure still assembling itself billions of years after its birth. And while Gaia mapped our home, another new mission looked outward again, toward the cosmic web itself. In 2023, the Euclid Space Telescope, another European Space Agency mission, was launched to explore one of the universe's greatest mysteries: dark energy, the invisible force driving the universe's accelerated expansion. Named after the ancient mathematician who defined geometry, Euclid's mission was itself geometric, to measure the shapes, distances, and clustering of billions of galaxies, and from those patterns infer the nature of cosmic acceleration. Euclid's instruments combined optical and infrared sensors, surveying vast swaths of sky with precision. Over 6 years, it aimed to chart over a third of the entire sky, cataloging billions of galaxies up to 10 billion light-years away. Its purpose was not to photograph beauty, but to decode structure, to turn the chaos of light into mathematical order. Together, Hubble, Webb, Gaia, and Euclid form a constellation of human curiosity, each complementing the others. Hubble showed us what the universe looks like. Webb shows us how it began. Gaia tells us where we are within it. Euclid tries to explain why it behaves the way it does. They are the four eyes of modern cosmology, each capturing a different truth about reality, each extending the legacy of those who once debated whether other galaxies even existed. And still, the question deepens. For as these telescopes look farther, they also reveal the limits of observation itself. Even the most powerful eyes cannot see beyond the edge of the observable universe, the horizon set by the speed of light and the age of time. In that sense, every telescope is both an instrument and a mirror. It not only looks outward, but reflects inward, showing humanity its own hunger to understand. Hubble's first deep fields were 10-day exposures. Webb's extend that into weeks, sometimes months. Euclid will survey for years, and the data it returns will take generations to interpret. Each pixel of cosmic light carries a story billions of years old. This is how the universe reveals itself, not all at once, but piece by piece, through the eyes of machines we built to replace our own. And yet, for all their complexity, these observatories share the same origin as the first telescopes of Galileo and Herschel: a simple act of wonder, a lens, a mirror, and a question: what lies beyond? The answer, it seems, is everything. As the 21st century unfolds, the frontier of cosmic mapping stretches ever wider. Upcoming missions like NASA's Nancy Grace Roman Space Telescope promise to continue this lineage, its wide-field infrared eye capable of imaging whole regions of sky at Hubble-like resolution. Combined with AI-assisted analysis, these instruments will not just observe the universe, they will simulate it, reconstructing cosmic evolution from its birth to its present. The great journey that began with Hubble's glass plate of Andromeda has become a digital symphony. Petabytes of starlight converted into mathematics, streamed across space, decoded by supercomputers, and rendered into images of breathtaking realism. Yet behind every pixel is the same fundamental human act: looking up and asking why. These telescopes are humanity's time machines. They show us the universe not as it is, but as it was, each photon a messenger from the past. Through them, we have seen galaxies colliding, stars forming, and light that began its voyage when Earth itself was still molten. And as our gaze deepens, a new realization dawns: that seeing is not understanding. The more we observe, the more mysterious the universe becomes. Dark matter, dark energy, the curvature of space, all point to a reality larger than comprehension. Still, we keep watching, because somewhere beyond the horizon of knowledge lies the reason we began to look in the first place. The telescopes orbit silently, far above the noise of Earth, sending home the faint signals of eternity. Their images are humanity's collective memory, proof that we once dared to reach into the infinite. And now, with the instruments aligned and the universe mapped in light, the next step begins, not just to look at galaxies, but to fly through them. To fly through the universe, one must first learn how to measure it. Light becomes our map, distance becomes time. Every photon that reaches our eyes, or our soul, structures. These variations are the fossil traces of quantum fluctuations stretched to galactic scales by cosmic inflation. From here, we look back. The entire history of the universe is laid out before us like a cosmic timeline. Closer to us, we see mature galaxies forming intricate clusters. Farther back, we see the young universe, galaxies smaller, bluer, more chaotic, still assembling themselves from primordial gas. Beyond that lies the cosmic dark age, when no stars had yet formed and hydrogen clouds filled the void. And before even that, light itself first escaping matter's grasp, revealing the surface of last scattering that gave birth to the microwave background. We are now at the frontier of observation, the edge of the observable universe. It lies about 46.5 billion light-years away in every direction, defining a sphere roughly 93 billion light-years across. This is not because the universe is 93 billion years old, but because space itself has expanded while the light traveled. Beyond this horizon, galaxies recede faster than light due to cosmic expansion. Their signals will never reach us. They exist, but they are forever unseen. Here, at the very boundary of what we can know, light fades into invisibility. The cosmic background stretches to wavelengths so long they blend into radio silence. Time and distance begin to merge. The early universe becomes a smooth field of potential, matter and energy indistinguishable. We have reached the farthest frontier, where even imagination hesitates. The observable universe ends not with a wall, but with a whisper. The light grows faint, the density uniform, and beyond lies darkness we cannot measure. And yet, the silence here is deceptive. Beyond our horizon, space continues, perhaps infinitely. There may be countless other regions, each with their own galaxies, stars, and laws of physics. Perhaps other observers, far beyond you, or reach, are making the same journey in reverse, looking toward us, seeing our Milky Way as a faint red speck at the edge of their visible cosmos. If so, then our universe is not a singular bubble, but one among many, a cosmic archipelago without shores. We hover at the edge for a moment longer, suspended between what we know and what we can only infer. The view is overwhelming, billions of galaxies filling a finite sphere, each containing trillions of stars, each star potentially holding worlds like ours. Every point of light is a story that has already ended. Every photon that reaches us has traveled through cosmic storms, gravitational fields, and epochs of expansion to arrive in this single instant. To fly through every galaxy is not merely to see distance, it is to witness time itself unfolding. These are not idle speculations. They are the logical extensions of the data, the whispers that emerge when we listen closely to the light. And so, we keep listening. The telescopes hum quietly in the vacuum. The radio dishes turn like patient ears, sweeping across the sky. The algorithms decode the spectra, line by line, translating cosmic symphonies into numbers. Each number is a distance. Each distance is a time. Together, they form the great cartography of existence, the bridge between what we can see and what we can only imagine. From Hubble's glass plates to Gaia's digital sky, from Penzias's static to Planck's precision, the path of discovery has been unbroken. Humanity's instruments have become extensions of its own perception, stretching the senses beyond the limits of biology. And now, as our technology grows still more powerful, we approach a threshold. Soon, telescopes like Gaia, Square Kilometer Array, will listen to the universe in radio waves with a sensitivity 100 times greater than anything before. They will detect the whispers of hydrogen from the first cosmic dawn, mapping how structure emerged from darkness. In parallel, gravitational wave observatories like LISA will listen to the fabric of space-time itself, detecting the ripples left by colliding black holes and merging galaxies. For the first time, we will not only see the universe, but hear it. Light, sound, gravity, all woven into a single cosmic narrative. The dream that began with a blurry photograph of Andromeda now spans every wavelength, every particle, every dimension we can reach. Our instruments have turned the sky into an open book, and we are only beginning to read its first chapters. The next chapter, our journey through that cosmic web, awaits. A flight not through imagination, but through reality itself. To travel through the universe is to travel through our own understanding of it. The fart, yurim yan. There we go, the smaller we become. Every new telescope, every deeper survey, expands not only the map of the cosmos, but the map of humility within the human mind. When we peer into the deep field, seeing thousands of galaxies crowd a single speck of sky, something ancient stirs in us. Awe, a word that once meant both wonder and fear. The realization that we exist in a universe too vast to measure, too old to fully know. A universe that was creating stars before our sun existed, that will continue long after our planet has turned to dust. Each ripple marks a place where gravity gained a small advantage, where matter gathered ever so slightly more densely than elsewhere. Over billions of years, those tiny differences would grow into the grand cosmic web we now see. From the soft unevenness of the CMB came everything: stars, planets, and life itself. It is here, within these ancient fluctuations, that our story truly began. The atoms in our bodies once swam in that primordial plasma. The same light that shines upon us now once scattered off the very particles that would one day become us. In this way, the edge of the observable universe is not a boundary at all. It is a mirror showing our own origins. But the universe does not stop at what we can see. Beyond this horizon, space continues. It expands faster than light, carrying distant galaxies away so swiftly that their signals can never reach us. For them, we are invisible too. Their skies contain their own horizons, their own cosmic edges. To imagine what lies beyond is to step into the realm of theory and imagination, where physics bends into philosophy. Some cosmologists propose that beyond our horizon lies more of the same, an infinite continuation of galaxies, repeating endlessly, like tiles in an infinite mosaic. Others suggest that the cosmos beyond may differ entirely. Regions with different physical constants, where atoms form differently, where gravity behaves otherwise. This idea, known as the multiverse hypothesis, paints a picture of reality not as a single universe, but as a boundless foam of universes, each bubble born from its own moment of inflation. Some may have expanded faster, others slower. Some may contain familiar physics, others not. And we, within our observable bubble, can never reach the others, forever separated by distances that grow faster than any speed we can imagine. Whether this is true or not, the edge we now face remains the jwst, greatest mystery in science. It is not a wall, but a veil, a transition between the known and the unknowable. Behind it may lie endless repetition or something wholly alien, but even without seeing it, we feel its presence. Every photon that reaches us has crossed that vast divide, whispering that there was once a time when the universe was small, hot, and bright, and that everything since has been expansion, cooling, and creation. As we hover at this limit, we begin to sense another truth. The farther we look outward, the farther we look inward. Because beyond this horizon, beyond even time's first light, there was no space as we know it, no matter, no form. There was only potential, quantum fluctuations in an unthinkably dense field. Then, in an instant of unimaginable brevity, expansion ignited. The universe inflated from smaller than an atom to larger than a galaxy in less than a trillionth of a second. That moment, cosmic inflation, created everything that would ever exist. It set the stage for matter, energy, gravity, and light. It defined the shape of space itself, and yet, it remains one of the most mysterious processes in all of physics. We know it happened, but not how or why. Science gives us numbers. Philosophy gives those numbers meaning. The light that strikes a telescope mirror tonight began its journey billions of years ago, before humanity, before Earth itself. To observe it is to witness a ghost. Every galaxy we see is already history. The cosmos we photograph is not the present, but a layered record of the past, stretched across time like a vast cosmic memory. In that sense, astronomy is not about seeing what is, but what was. Every photon is a messenger from a vanished moment. We are the only species, as far as we know, that can decode such messages and understand that they come from a universe indifferent to whether we exist or not. It is humbling, but also beautiful, because in that indifference lies meaning we create for ourselves. The night sky becomes not a void, but a mirror. For centuries, philosophers argued about our place in creation. The Greeks saw perfection in circles, the heavens moving in eternal harmony. Medieval thinkers saw divine architecture, the clockwork of a creator. Modern science stripped away both notions, replacing purpose with process, creation with evolution. Yet somehow, that shift did not diminish wonder. It deepened it. The idea that we are made of stardust, that the carbon in our bodies, the calcium in our bones, the iron in our blood were all forged in ancient stars, connects us to the universe more intimately than myth ever could. We are not separate from the cosmos. We are expressions of it. The universe is not out there. It is within us. Every galaxy is a possibility of life. Every star is a potential sun. Every planet a chance for meaning to arise again. The universe may be vast and silent, but it is also fertile, endlessly generating new forms of complexity, from hydrogen clouds to human consciousness. That consciousness, fragile and finite, becomes the instrument through which the universe perceives I, self. The poet Rilke once wrote, "For beauty is nothing but the beginning of terror we are still just able to bear." Astronomy lives at that boundary, between knowledge and mystery, between data and awe, between seeing and understanding. We measure redshifts, map filaments, calculate mass densities, but behind every number is a question that science alone cannot answer. Why is there something rather than nothing? Some physicists suggest that the universe is simply one of many, that infinite others exist beyond our observable horizon, each with different laws of physics, different constants, perhaps even different versions of ourselves. Others propose that the universe is a quantum fluctuation, a brief awakening from nothingness, destined to fade again. Dimensional atlas of cosmic evolution, showing how structure formed from the CMB's tiny fluctuations. Together, Webb, Roman, Rubin, Gaia, Euclid, and Gaia form a single coordinated vision to turn the night sky into a measurable, evolving system, not just to look at galaxies, but to understand their relationships, their orbits, their collisions, their collective behavior within the cosmic web. And beyond even these missions, others wait on the horizon. NASA's LUVOIR concept, if realized, would be the largest optical space telescope ever constructed, with a mirror up to 15 meters wide. It could image Earth-like planets around distant stars, resolving oceans and continents as faint reflections of sunlight. ESA's proposed LISA mission, Laser Interferometer Space Antenna, will detect gravitational waves from orbit, listening to the ripples of merging black holes billions of light-years away. Where telescopes see light, LISA will hear space-time itself vibrate. For the first time, we will observe the universe through every possible medium: light, gravity, neutrinos, and even cosmic rays, combining them into a multi-messenger view of reality. This synthesis will mark a turning point, from isolated observations to unified cosmic sensing. On Earth, the Extremely Large Telescope, ELT in Chile, its mirror, a staggering 39 meters across, will complement space missions with adaptive optics so precise it can resolve details on exoplanets light-years away. Across the ocean, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will join it, forming an intercontinental network of precision instruments capable of probing the early universe and the atmospheres of alien worlds. And as these observatories multiply, so too will our ability to visualize their findings. Supercomputers like Frontier and Aurora already simulate the universe's evolution across billions of years, from the Big Bang to now. With quantum computing on the horizon, these simulations will soon include every force, every interaction, replaying creation not as a metaphor, but as a measurable event. Through these simulations, we can fly through galaxies not as imagination, but as physics itself, a data-driven reconstruction of reality, accurate down to the motion of each cluster. What began as artistic visualization will become scientific navigation. AI will learn not just to analyze the universe, but to predict it, to model how galaxies evolve, where new stars will form, and how cosmic filaments will stretch as expansion continues. Already, neural networks trained on sky survey data can classify galaxies better than human experts, spotting patterns we never noticed. Soon, they will guide telescope targeting, directing our gaze to regions of greatest interest, even before we know why. In a sense, the machines are becoming our cosmic intuition, our extended senses across light years, But even if those ideas prove true, the experience of standing beneath a clear night sky remains unchanged. The human heart does not measure wonder in equations, it feels it. That feeling is universal. From the first cave painters tracing constellations on stone to modern astronomers aligning mirrors in orbit, the act is the same: to look up and find meaning in the infinite. The farther we see, the more we recognize how much remains unseen. The edge of the observable universe is not a physical wall, it is a boundary of comprehension. Beyond it, light has not yet had time to reach us. There may be countless galaxies beyond that edge, but they exist forever beyond our observation. This limitation is not a failure. It is the universe's way of reminding us that mystery is part of its design. Every discovery widens the circle of the known, but the circumference of ignorance grows even faster. And perhaps that is what keeps us exploring. If we could see everything, we might stop looking. The philosopher Carl Sagan called humanity the cosmos trying to understand itself. He saw exploration not as arrogance, but as destiny, a natural consequence of consciousness. To be aware is to be curious. To be curious is to reach outward. When astronauts orbit Earth and see its fragile blue arc against the black, they describe what's known as the overview effect, a sudden shift in perception. Borders vanish, conflicts shrink. The planet becomes one organism, alive in a sea of silence. It's the same effect, magnified, that the cosmic perspective brings, a sense of unity not through dominance, but through shared smallness. From that vantage, human divisions, race, nation, creed, seem almost absurd. The light from a single star has traveled across billions of years. What then is a lifetime? What is a war? And yet, the same species that splits atoms and quarrels over borders has also built instrument, is capable of seeing back to the dawn of time. That duality defines us. We are both fragile and magnificent, tiny in scale, infinite in imagination. Perhaps that is the universe's hidden symmetry. It balances its vastness with our capacity to perceive it. To look across billions of light years and feel something is not trivial. It is extraordinary. The human brain, evolved to survive in forests and fields, now maps superclusters and models dark energy. Our tools extend our senses, but our senses guide our purpose. In the quiet data streams of observatories, meaning flickers, fragile, subjective, but real. The maps we make are also maps of ourselves, darkness, absolute and endless. Then, one by one, points of light ignite like scattered embers. Each flare is a galaxy, each galaxy a city of suns. The camera drifts outward silently, beyond the swirl of our own Milky Way, its spiral arms curling like luminous smoke against the black. 100 billion stars fade beneath us. Beyond them, another 100 billion galaxies. We pass the faint blue arc of Andromeda. The local group becomes a cluster. The cluster becomes a supercluster. Threads of matter weave into filaments, vast cosmic highways where gravity sculpted light into structure. Between them lie voids, colder than imagination, stretching for millions of light years. Our view accelerates. In seconds, we cross distances no spacecraft will ever travel. Galaxies shrink to specks. Superclusters form a cosmic web glowing faintly in microwave light, the fossil afterglow of the Big Bang. We're still inside it, yet already witnessing its edge. The entire observable universe floats before us, a sphere 93 billion light-years wide, fragile and finite, suspended in an ocean of unknown darkness. And somewhere, hidden within that ocean, is us, a species staring outward, wondering how far this light goes, and what lies beyond its reach. This is the map of everything we can see, and tonight we will fly through it all. For most of human history, the universe seemed small enough to imagine. The stars were tiny lamps hung on a distant ceiling, fixed and eternal. The Milky Way, its pale band crossing the night sky, was thought to be the limit of creation itself. To the philosophers of ancient Greece, it was the edge of a finite cosmos. To medieval astronomers, it was the heavenly dome, enclosing all that existed. Even as telescopes began to probe the heavens in the 17th century, that belief remained largely unchallenged. The Milky Way was seen not as one galaxy among many, but as the univee, Earth's entire, Stars, clusters, and faint nebulae all were assumed to belong within its borders. The universe, in human understanding, ended just beyond its rim. Then, in the late 19th century, the question began to shift. Astronomers using larger and more refined instruments noticed strange spiral forms scattered among the stars. Through the eyepieces of observatories in England, France, and the United States, these spirals appeared ghost-like, tiny whirlpools of light, faint and unresolved. Some called them spiral nebulae. No one knew what they were. Were they gaseous clouds forming stars within our own galaxy? Or were they, impossibly, entire star systems themselves, so distant that their light took millions of years to reach us? It was a question that divided astronomy at its core. And just as Galileo's lens extended human vision 4 centuries ago, AI extends our perception across time. But beneath all the computation and data lies something deeply human. Each new mission, each new map, begins with the same simple impulse: curiosity. It is the same curiosity that drove Hubble to measure Cepheid stars, that sent Webb 1 million miles into the dark, that inspired generations to climb mountain observatories through freezing nights just to glimpse a faint blur of light. That impulse is our true instrument, the one that builds all others. The future of astronomy will not be defined by a single telescope, but by a network of minds and machines working together to chart the infinite. Every byte of data, every pixel of light, is another coordinate in humanity's growing map of existence. We are turning the universe into something measurable, but also something personal. When Hubble looked at Andromeda, it redefined space. When Webb looked at SMACS 0723, it redefined time. The next telescopes may redefine consciousness itself, forcing us to confront what it means to know, to observe, to exist in a universe that continues to create even as we study it. Cosmic cartography has always been more than science. It is a mirror of civilization. Each new map reflects not just the structure of the universe, but the structure of human ambition. The early star charts of Babylon mapped myth. The telescopic atlases of the Enlightenment mapped discovery. The digital surveys of today map truth. And the maps of tomorrow, rendered in AI, layered in 3D, navigable in real time, will map something deeper: connection. Because when we trace the filaments of the cosmic web, we are also tracing the filaments of our own history, how thought and technology intertwine across generations, linking us to those who first looked up. One day soon, every person with a computer or headset will be able to traverse the universe virtually, flying through the real positions of galaxies, guided by actual data from Euclid, Gaia, and Gaia. The cosmos will become explorable, not just as a concept, but as a shared experience. And when that happens, astronomy will no longer belong only to scientists. It will belong to everyone. Children will drift through galactic clusters in classrooms. Artists will sculpt constellations from raw data. Historians will trace the evolution of galaxies like genealogies. The night sky will become an open archive of knowledge and wonder.